So I think we can go ahead now that the person is connected. Martin, are you there? I think we lost Martin. Martin?
Yeah.
Martin, are you there?
Yes, I'm there.
We lost you for a second, so I will pay attention in case that this happens again, but we lost you for a second. Okay,
Yeah.
so Nuria, I think we can start recording.
Yeah, I started.
Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. So today we are extremely pleased to having Martin Schmidt, who is a full professor of nonlinear optimization at the University of Trier in Germany, and he is also a fellow of the Energy Campus in Nuremberg. His fields of work include mathematical modeling and optimization of energy systems with a focus on mixed integer, nonlinear, and multi-level modeling. So he has done work on gas transportation networks and on energy markets, but also on machine learning, as you will see today. So his research has appeared in leading journals in the field such as Mathematical Programming, European Journal on Operations Research, and Science Journal on Optimization. And he has received various awards for his research, such as the Euro Excellence in Practice Award in 2016 and the Margaret Frank Award for the best paper in the Euro Journal on Combinatorial Optimization in 2021. Martin is regularly invited to give talks and he has talked at the Euro Conference 2022 in Finland, where he was a keynote speaker, and very recently over the summer he was also a plenary speaker at the International Conference on Bi-Level Optimization. He is also very committed to serving the community, and he is in the editorial board of several journals, such as the Journal of Optimization Theory and Applications and the journal Euro Journal on Computational Optimization. So we are very pleased of having you today here. So the floor is yours, and Martin has agreed that you can ask the questions on the go. So I suggest that you put them in the chat and I will read them out to him. But at the very end, we will also have time for questions. Thank you very much again, Martin, for coming today.
Yeah, thank you very much. First of all, for the very nice introduction and also for giving me the opportunity to give a talk today in this very nice online series of seminars. So I will try to organize my screen here a bit. So you see my screen on full screen, all is working?
All is working.
Okay, perfect. Good. Yeah, so my topic today is the minimum sum of squares clustering problem. And this is a very well-known topic in machine learning, in applied statistics and computational statistics. But I will try to talk about two things or two aspects of this problem that are not so, I would say, standard. One is to consider robustified versions of this problem. And robustified, I mean in the sense of robust optimization. And I will also talk a bit about solving these problems to global optimality, which is often not done in practice. So before I really start, I have to say that the people that you now see on the screen are the four people who really should get the credit for all the work that I'm presenting today. And most of it was in the PhD thesis of Carina Costa. So she is the main working horse behind all this work here. Okay, so this is the agenda of my talk. This looks like a lot of sections, but they will not be too long, so I will try to stay in time. And I mean, in the beginning, I will give you a motivation, an introduction, a first modeling of this problem that we will then use for developing robust counterparts and later on also for global optimization. Good. So what is the MSSC problem? So the minimum sum of squares problem. Well, we are given n data points in some RD, And we have a certain number of clusters given. We call this K. And the question is that how can you assign every of these data points to exactly one cluster? And how can you find a representative for every cluster so that this representative covers, I would say, the main aspects of the data point for which this is actually the representative. I will make this, if you don't know the problem anyway, a bit more clear later on with some more specific definitions and also pictures. And as most of you, I guess, know, this is a key problem in unsupervised machine learning. It's unsupervised because we don't know which point belongs to which cluster beforehand. Okay, so we have, in some sense, no labels given. So this is why we are in the field of unsupervised machine learning. So a little bit more formal, these representatives that I have been talking about, I also call them centroids because they will be kind of the mean points in the clusters that we're going to find. And these centroids should be so that they minimize a certain, let's say, loss function. We call this h here, and this h depends on c, so the vector of centroids, and also here on the given set of points p. And the question then, of course, is what is h? What is the loss function? And I define it here. So we sum over all the clusters that we have, and then we sum over all the points p that are assigned to the cluster pj, and then we minimize the two norms squared of the difference between the point and the chosen centroid. And of course, this is kind of a cheating formulation because the main difficulty in solving the MSSC problem is to find out what is actually this set pj here. So which points are assigned to which cluster. But on a, let's say, phenomenological level, this is what we're going to do. And it's getting, I guess, even a bit more clear if you take a look at some pictures. So at the left-hand side here, you see blue points, and some of them are a bit denser. Then you have some overplotting, and the blue gets a bit darker. And of course, just by looking at this example in 2D, you see that there are 8 clusters, and the black crosses that you see, I mean, are proper, I mean, visually speaking, proper centroids or representatives of the data points in the respective clusters. But, and we will come back to this point later on, you can also have the same set of data points, but a bad clustering. So you here in this example, you split this cluster over there in 2 clusters having 2 centroids. And on the other hand, you merge these 2 clusters, which are clearly separated in a visual way, and have only 1 cluster here. We will later come back to this point because on the right-hand side, what you see is kind of a local minimizer of the problem, which is a non-convex problem. So there are very bad local minimizers, and global optimization is a very important topic here because you don't want to work with the clustering on the right-hand side. You want to work with the one on the left-hand side. So the areas of application are, I mean, numerous. There are tons of different applications. So depending on what you model with the different components of your points in RD, which could be gender, age, income, whatever you want to study, you have very many different possibilities on what to tackle with this kind of problem. So it ranges from data analysis over bioinformatics, economics. It's very often used in social sciences if you have some classic surveys, for instance, but also in energy models, it's used more and more often. So this is by far not a comprehensive list here, but just exemplarily showing how diverse the fields of application actually are. So coming to how difficult it is to solve these problems, the theoretical complexity result is that this is NP hard already in 2 dimensions. Okay, so this has been shown for the first time by Dasgupta. There was a tiny bug in the proof. This was fixed by Aloise and co-authors a few years later, but there are also other proofs that appear again and again with different techniques from time to time. So it's for sure NP hard, and at least, I mean, I will tell you a bit about the global optimization results later on. I was really shocked on how difficult this problem is when you really want to solve these instances to global optimality. Later, more on that. So because it is so hard, people usually in practice, if they have large scale applications, they don't use exact approaches, but they use heuristic approaches. And the most famous one, I guess, is the so-called k-means clustering problem, which is just an alternating method where you alternate between choosing an assignment of points to clusters and then find new centroids, then you find a new cluster, you find a new assignment, and you iterate. So this is the very, very famous heuristic to solve these problems, at least in a local or heuristic sense. So if we are going to study this with respect to robustifications and global optimization, we have to write down an MINLP model for it. It will be an MINLP model, and the modeling is really straightforward, so I can do this rather quickly here. So what you do is you introduce binary variables indexed with P for the point and J for the cluster, and it has the meaning that whenever this variable with index P and J is 1, it means that you assign the point P to cluster J, 0 otherwise. Okay, that's easy. And you can with this also get rid of the cheating that I mentioned before in the objective function, because you can now really state H here, the loss function. So you now sum over all the clusters, over all the points, and now you only take this square of the 2 norm of the difference here into account if your binary variable tells you that P is actually assigned to cluster J. And of course, we have an SOS1 kind of constraint that says, okay, we can only assign a point to 1 cluster. So that's pretty easy, and that's it. Okay, this is the overall problem. It looks very simple. As I said, if you want to study this from the global optimization point of view, it's really, really annoying. So a few characteristics. Why is it hard? Of course, it is hard because you have this kind of assignment problem inside that you model using mixed integer, or in this case, integer variables. And if you write down the model as I did it here, you have a nonlinear, because of being cubic, non-convex objective function. Okay, it's cubic here because you also have x as a variable and the CJ here, the centroids, as a variable. We'll come to other formulations later on, but this is, I would say, the first model that you write down when you start working on that problem. Okay. I hope this is clear so far, because we will now take this model and study robustified versions of this model. So we want to apply robust optimization to this MSSC MINLP. And of course, the question is, why do you want to do so? And from my point of view, this is very much reasonable, because in practice, what you get as an input for your problem are the data points, the P, okay? P here is again kind of the set of points, but what you usually get in practice is not exact data that is without any errors, let it be measurement errors or incompletely filled surveys or whatever. So there are very many different reasons for why you might have errors in your data. So what we do here is we say, okay, we don't know the actual data P, but what we observe is a kind of a perturbed data set, P tilde. And P tilde is constructed, or is obtained from P by an additive error here, capital E. So capital E then is a matrix of perturbations of the original data. And since I have no idea, no clue about stochastic optimization, let's do it in a robust way here. So we want to make the assumption now that we don't have any distributional information on the data. But it's not just because I have no clue about stochastics. It's also that in very many situations, for instance, if you have incompletely filled survey data or whatever, you actually do not have any distributional information. So the robust approach actually makes sense here. Okay, and now comes the main kind of motivation or idea. Although you can only observe the erroneous data, P tilde, you of course still want to find a clustering that is a good clustering with respect to the original data. So the unperturbed data, because this is the data that you really want to understand, where you want to see what is the structure, etc. Okay, and this, of course, I agree at that point. This sounds a bit like black magic, right? I mean, you only see p tilde, but you want to have a clustering for p. And I will show you in a few minutes that robust optimization can do the job. Okay, it does not always work, but we will discuss this. It can work very well. So how do we formalize this? Well, we still minimize in our robustified counterpart here over the centroids, but now I just take, let me go one slide back, I just take this equation and solve it for p. Then I have p tilde minus the error, and now I don't have a specific error anymore, but I take the maximum here over all possible errors. It's getting a new name, d in some uncertainty set script u. So this is now what we want to solve if we tackle this problem from the robust optimization point of view. So we still want to minimize over the centroids, taking into account the potential errors in your measurements or whatever, and this you do in a worst case sense. So you consider the case in which the data is realizing in the worst case sense in terms of your objective function, which is our loss function here in this setting. And for the moment, u is just some uncertainty set that is given. And for the ease of presentation, but I will not go into the discussion of all these details, it's just about boxes. So for every point we say, okay, there is a box around this point and we don't know exactly where the point is, but we assume that it is within this box. Okay, so it's a classic robust optimization problem with box uncertainties. Good. So then if you write this down in a bit more specific way, this is your robust counterpart. And since we actually consider the real worst case here, this is also what's called the strictly robust counterpart, or the static sometimes in some books or papers. So you really take the worst case realization here by considering this min-max structure where the inner max is the maximization over the uncertainty set. And you again have then here this difference between the point and the perturbation. Okay, the constraints stay as they are because they are not affected by any uncertainty due to the modeling of the problem itself. Good. The problem, let me go one slide back. The problem here, of course, is that this is a min-max structure and this is difficult to deal with in general, okay? The nice thing here is that the structure is easy enough so that you can get rid of the inner maximization problem. So you get a problem that is what we then call the robust counterpart here, which is equivalent to this, again, kind of single level optimization model. It's getting more complicated. You get some more terms, but it's still just a minimization problem, a mixed integer nonlinear one as before, just larger, but polynomially larger. It's not exploding. Okay, so I'm not going into the details on how to arrive from this min-max structure to this min structure. I can just tell you it's the classic standard tricks of robust optimization. Mainly, you dualize the inner maximization problem to get rid of it. So it's just an easy exercise in taking a dual of a linear optimization problem. Well, and we can try to solve this, of course. We will do this later on. But we also said, well, okay, in robust optimization, there is not only strict robustness, but there are also other things. And there are other things because strict robustness has been criticized a bit or a lot because the people or many people said that it's just too conservative. So we get too worse objective function values because we really have this worst case philosophy behind. So there are relaxed concepts. Two very famous ones are, for instance, gamma robustness by Bert-Siemens and Zim, and there is also adjustable robustness. And our alternative approach now, in what I will show you in the following, is the gamma robust counterpart. So how does this lead to something that is less conservative? Well, you take your old uncertainty set here, and you just restrict the number of components of points for which the uncertainty actually realizes, so for which the uncertainty is non-zero, to being or having cardinality less than this given gamma. So you don't say everything can realize in a worst case way, but just gamma many parameters can realize in such a bad way. Okay, and then you can write down this gamma robust counterpart. I'm not going into the details here. It's just like you take with this inner maximization problem here, the worst case about gamma many realizations of uncertainty, and the rest is just straightforward modeling. It looks complicated because there are many terms, but it's not, okay? So it's the classic way on how to derive robust counterparts here. Good. Again, you have a min-max structure, which is ugly, but I mean, with classic tricks from gamma robust optimization, you can get rid of the inner maximization problem and you get a problem that is in the same class of problems as the nominal one that you started with, but being larger. Okay, so again, this looks complicated. I'm not going to discuss the details. I mean, if you're really interested in it, you can ask questions about it, and then I will try to, but the details don't matter too much here right now. Good. So how to solve these problems, okay? I said already that the nominal problem is NP hard, so the robust counterparts have to be NP hard as well in these situations. And well, solving these things to global optimization, when we started with this, we said, okay, it's too hard, let's not do it. So we just try to develop tailored heuristic methods to solve these robust optimization problems. And well, this is a bit of a heretic comment here. What we actually did is we kind of rediscovered something and give it a different name. I would let you know what I mean with this in particular. But the good thing is that, I mean, we kind of rediscovered k-means clustering that I explained to you a bit before, but in a way that it allows for generalizing it to the robust settings, okay, which is not directly possible with the k-means algorithm from the literature. So ADM here stands for an alternating direction method, and I will give you the very basic things in a few slides here. So assume you just have an optimization problem in two different blocks of variables, u and v, and you have some disjoint constraint sets, capital U and capital V, and you have some, I will call them coupling constraints. So those constraints that actually couple U and V. And we will make some standard assumptions, which are mainly the assumptions of the theorem by Weierstrass that ensure us that there exists an optimal solution. So continuity of all the functions and that all the sets are non-empty and compact. Well, and then the method is super easy. Don't read this slide. I will tell you what's written there in words, and then it's easier to understand. So you have a starting point for U and V. Fix V for the moment, and just solve in the direction of U. You get a new point for U, you fix this, you solve in the direction of V, you get a new point for V, you fix this, and you iterate. That's it. This is why it's called an alternating direction method. Sometimes it's also called like block coordinate descent, or if you go to the extreme, then you have coordinate descent. So there are different, well, names of these methods in practice. And there are some theorems telling you that if the classic assumptions that I just made on the last slide are satisfied, then you get convergence to something, and this something is a partial minimum here, okay? And this partial minimum is a very weak optimality concept. So it's even weaker than local optimality. And I will come back to this point later on. It's related to what you saw in the very first pictures where I showed you a bad local or partial minimizer of the problem. So what do we get? So we just took this method and we applied it to the robust counterparts. Of course, in order to do so, you have to find a clever split of your entire variable space. And the original thing with the k-means clustering is that you get the k-means clustering if you just split the variables for the assignment, so the integer variables, from the continuous variables for finding the centroids. So then you find a new centroid. If you have it, you find a new assignment. If you have it, you find a new centroid, and so on. So this means that the k-means clustering method is nothing but an alternating direction method with a proper variable split. And we mainly stayed with this way of splitting the problem so that you really split between continuous variables and integer variables. So this is one of the test sets that we use. And I will try to give you an idea or an intuition for when can this robustification actually help to get better clustering results. So if you take a look at these two different data sets for clustering, they are what I would informally call well separated. So you rather clearly see clusters, right? If you now take, for instance, one of these points here and perturb it a bit, it will not change the overall clustering because the data set is, again, well separated. And I mean, this is an informal definition now of what you see here, but I guess that you have a good idea of what I mean. In such a situation, I would not expect that robust optimization in the way that I presented it will actually help. However, if you have data sets that look like this, I won't call them well separated in some sense because, well, I don't see clearly clusters or how many clusters I actually have. Okay, so with these data sets, I think that you should get maybe an impact of a robustified model in it. Good. Is there any problem?
Yes, apparently a couple of people got stuck in slide 20. So apparently their connection was a little bit not allowing them to progress. So yeah, but I think now I saw Paula saying that it's sorted. In general, please remember to enter. Yes. So remember to enter again if your connection gets stuck.
Okay.
So some people said that they missed slide 21. So maybe you can say a few words. Yeah.
Okay. I would like to repeat this because this is really important because I want to kind of convey
so much.
The main ideas here. So here on slide 21, I showed you two instances for a data set for clustering. And I would call them well separated. This is not a formal notion, but it means that you clearly see clusters, okay? You can count now and you would come up with a good idea on how many clusters there are and which are the points that belong to which cluster. In such a well-separated situation, I would not expect that the robustified version of the problem would give you something really different. If I now take one of these points here and just perturb it a bit, it won't change the outcome of the clustering very much. However, these data sets here are not well separated in the sense that I just explained. And I think that here, robust optimization can really find or help to find good points. So we took this data set by Frenti and Siranoia, and I show you some examples for the results here for the blue instances. So I'm not considering in this talk all the instances from this data set for clustering problems. And let me first tell you a bit about the complexity. So on the left-hand side here, you see for the different instances, the running times for the nominal model, the strictly robust model, and the gamma robust model. And you see nominal is much easier to solve than strict robust, is easier to solve than gamma robust. Okay, however, if you take a look at the iteration count, you see that they are almost constant. So it's not that the ADM that I was talking about, so these are ADM iterations, are more, but each iteration itself is taking longer because the models that we have to solve, they get larger and even also more complicated. Okay, now I would just want to give you one result that shows how well this can work. So what did we do? We take this instance with the blue points that you see on the left-hand side, and the green triangles are the ground truth. So these are the real cluster centroids. So what we did is we took these blue points and we perturbed a certain number of the points, I guess something like 50%, by 10% of the point's magnitude. So the box is kind of 10% of the point's values. And then we took these perturbed instances and we applied the nominal version of the k-means clustering. And what we got are the black crosses. And you see that you can get a really bad clustering result if you have perturbed or erroneous data. But if you just consider them to be like the real data set. However, if you take a look on the right-hand side, we do exactly the same, but use the robustified version to solve the problem. And what you see is that you more or less perfectly get back the structure of the clustering for the real data, although you only considered in a robustified way the perturbed data. And this picture on the right tells you that it's actually possible with robust optimization to get a clustering structure for the original data, although you only see the perturbed data. Okay, so I'm not showing many more results here, but this picture I like a lot because it really shows how well it can work. And on the left-hand side, you see how bad it can be if you just assume that the data that you see is the nominal data. Okay, we did this also for the gamma robust approach, and the results were extremely bad. And the question then was like, wow, why? I mean, here, I mean, I'm not going into the statistical details. The closer the value is to 1, here, for instance, for the nominal or for the strictly, it's 0.9 something or 7 or 8.5. The closer to 1, the better your clustering is. And then we tested this for different values of gamma, and it was getting worse and worse. And interestingly, for gamma equals to 100%, you get this value, but this is mathematically equivalent to the nominal, to the strictly robust case. So we were wondering like, okay, what is wrong here? And what is wrong is that you just get, if you solve these more complicated clustering problems, very bad local minimizers. So we said, okay, maybe the gamma approach is not the problem, but the problem is that we don't know how to solve these problems to global optimization. So we started to consider this problem also from the global optimization point of view. And just want to give you, in let's say the last 10 minutes, a brief overview of the techniques that we developed. And of course, I think this is very important. I mean, as I said at the beginning, clustering is an unsupervised machine learning task. So usually, after the clustering, some experts from the domain, let it be doctors for cancer or whatever the application is, need to take a look at the clustering results. However, there can be very, very bad decisions based on what these experts see. If they see a bad local minimizer, if they have to draw conclusions, for instance, regarding the treatment of cancer, maybe it's even cancer, but they think it is because the clustering solution is so bad. Okay, so we want to have global optimal solutions. So convexity would be nice, but I mean, the problem that we are here considering is obviously not convex. So it's a real global optimization task. And here again is the picture from the very beginning. So what we want to avoid is a solution that you see here on the right-hand side, where you have a local minimizer that is really bad in the sense that you obviously, I mean, with our human eyes, we see that this is obviously not the right clustering, okay? We are not the first doing it. I mean, I would say that there are 3 generations of global approaches to clustering. The first one is just simple branch and bound, obviously. The second one is, and this mainly goes back to the PhD thesis of Danielle Aloise, is column generation. And I would say the most powerful way of solving these problems to global optimality today, and this is the paper here by Veronica Picciali and co-authors, is to do something like branch and bound, but based on SDP relaxations. Okay, so this is again just an exemplary list. It's not comprehensive. So one thing that we did when we started to work on this is we got rid of the cubic terms in the objective function. So we just have this kind of epigraph reformulation where we have this eta here and we minimize the old objective function by just putting this inequality constraint here in the constraints. It's a classic big M formulation. It's not cubic anymore. It's not non-convex anymore because you have the norm, which is convex here on the right-hand side. And you can easily find the big M values in this setting. That's all nice. Everything else stays mainly as it is. Okay, so this is what I will call the epigraph reformulation in what follows. So we try to develop kind of some different techniques here. And the first thing that you want to find is usually cuts. Okay, cutting planes. So there are some in the literature. I show you the so-called cardinality cuts. So for instance, you know that an optimal solution will never have an empty cluster. So you have this inequality as a valid cutting plane. And you also have this inequality by the same argument because you cannot have more than this right-hand side number of points in a cluster because then other clusters would have to have a zero number of points inside. So this is really easy. What we did, let's talk first about the things that didn't work that well. You can localize these cuts in the branch and cut method, but this didn't help much more. What we really found to be useful is, well, if you take a look at the epigraph constraint that I just introduced, this is a non-linear but convex constraint. So you can do outer approximation for it. So I like outer approximation already since a few years. So I wanted to use it here as well. And well, this is the cut that you get. Don't try to understand it. It's just like you take the classic first order Taylor approximation. And since this is a convex setting, after the reformulation, everything is fine. Okay. So these I will refer to outer approximation cuts later on. And one other thing that really helped us are propagation techniques. So what are propagation techniques? So think about this situation that you're somewhere in the branch and cut tree that you're considering. So at one of these nodes, you already have some bounds tightened, some variables fixed, and so on. And propagation refers to the technique that you take these reductions and you want to derive further reductions based on it. And there's one very big challenge, and this is why, in my understanding, the clustering problem is so difficult from the point of view of global optimization. And the reason is everything is feasible, kind of. I mean, the only real feasibility constraint is this SOS1 constraint here. It's more or less trivial. Yeah? So you cannot derive, let's say, cuts or propagation techniques based on feasible or infeasible situations. You always have to work on the dual bound explicitly in the sense that all your arguments that you want to develop need to be based on optimality because feasibility is never an issue. This is my intuition of why this problem is so hard. You just have to, you have a really hard time to get good dual bounds in your methods. So let me explain two propagators that we have. The first one is based on this lemma. So what you have here is if you have some clusters, so points, sets of points, and whenever you take the convex hull of one of these point sets and you intersect it again with the overall set of points, you get back Pj. What does it mean? It means that in an optimal solution, you always have something like a convex structure. So you cannot have a point assigned to another cluster within the convex hull of another cluster. This is what this equality tells you here. And this can be used very well. So if you have the convex hull of these points and you have a new point, well, either if your other constraints in the branch and cut tree tell you that this point cannot be assigned to this cluster J anymore, you can prune the node because it can never ever be part of an optimal solution because it violates this convexity property. On the other hand, you know that you can fix it to 1. You can make the decision. It has to be within the convex hull. So this is what we call convexity propagator. And done, I mean, of course, you have to be careful here, right? The convex hull is in higher dimensions can be hard to describe, of course. The other one is a conic propagation. So, I mean, one of our co-authors then came up with this one. So I, of course, didn't understand what's written there. I show you a picture that at least helped me to understand this propagator. Let's say you have these red points that are already assigned to, let's say, the red cluster. And now you take all the rays that you get from all these points through another point Q here. And then you get this cone, okay, of the black points. And what you know is if this point Q is not assigned to the red cluster, none of the black ones can be assigned to the black cluster. Excuse me, to the red cluster, okay? For the white points, you don't know, okay? So you have this cone here that you can use to derive further fixations if you have already some decisions made in your branch and cut tree. Okay, so some ideas, I just want to give you some idea about the numerical results as well. So we implemented this with Cplex as an LP solver within SCIP. So everything is open source here. You can get the codes on this GitHub repository of Christopher. And so it's everything available. You can test it if you want. This is the test set that we used. So this is from this UCML machine learning library. And these are the instances that I showed you before by Frenti and Sira Neuer. And well, we started, and this is now the moment where I realized how extremely difficult this problem is. We gave the plain model to SCIP, the original model that I showed you. SCIP in 1 hour, except for one instance here, the German 22, which it could solve after 900 seconds, always reached the time limit and had never a finite gap. I mean, I really didn't believe that these results are bug-free because I was not aware of that this problem is so hard to be solved to global optimality before. If you go to the epigraph reformulation, you still always hit the time limit, but you at least get a lot of finite gaps here. But to be honest, I mean, these gaps are super huge still, right? However, the instance that you can solve, you are much, much quicker just by changing the formulation so that you have an almost conic formulation. This is almost an SOCP formulation that I showed you before. So then we included some heuristics. We included the convexity and the cone propagator. And then we solved some more problems. And in the epigraph reformulations, we even got some better gaps, so it helped. By the way, what are the heuristics here? In the paper, it's written, I mean, you can use k-means clustering as a super quick heuristic. You can use rounding heuristics that are rather powerful, but these are really easy ideas, so I didn't talk about before about these things. It's mainly about the two propagators that help here to find more solutions and for some others at least get a finite gap. This one I skip. So if you then go to the outer approximation cuts, you see that it helps even more, although here on the left-hand side, this is the same result as before, because you can only apply the outer approximation cuts to the epigraph formulation of the problem, because otherwise you're not convex. So we almost always get a finite gap, but still, the gaps are huge, but we can solve more instances at least. Good. So last slide, just to wrap up. The first thing is, I guess in most of your applications that you study with something like a clustering problem, your data is screwed. And the results, this one picture in particular that I showed you, at least tells me we should tackle these uncertainties inside. And what I proposed here is a robust approach. And now comes the big question behind. And this is the why the hell does it work? I showed you this picture and I talked about black magic. I mean, it works, but if you would ask me for what is the mathematical, what is the structural reason for why this works, I have no answer. So this is for me really still open. And if we understand this better, we can maybe also get to better robustifications or other techniques to actually tackle the uncertainties inside. Of course, you can use other robustification concepts. You can use other norms, other uncertainty sets. So there is a lot of things to do if you find this interesting. But I think the really important mathematical question that would then help also for the application is, why does it work? Okay, or in which situation does it work well? Well, and on the other hand, I showed you that the gamma robust counterparts were almost not reasonably solvable because we always ended up with very bad local minimizers or partial minimizers. So I think that we should really, as a community, deal with these questions of global optimization of clustering problems much more. So, I mean, here, at least with our techniques, we get from almost nothing to at least something, but this is, of course, not the end of the story, okay? So there are still very many open questions, also algorithmic ones here. So maybe you can use our techniques, for instance, with some techniques in the literature that are there to reduce the dimension of the problem. So for instance, Leo Liberti did some works on that. You can maybe combine this with the state-of-the-art SDP approaches and put our cuts and propagation techniques inside. So there's still a lot of room for improvement. And yeah, I mean, if you're still searching for a proper PhD thesis topic, this is really interesting in my point of view, or from my point of view. It's super important because it has a lot of applications and the to-do list is still huge in this area. And with this, I think I'm done. And yeah, thanks again for the invitation and for listening. Thanks.
Thank you so much, Martin, for the great presentation and also for giving us some future view of the field. I believe that Salvador has a question. So Nuria, if you could give Salvador, say the rights to the camera and to the microphone.
I believe he can now.
Yeah, so Salvador, could you please go ahead?
Okay. Hi. Thank you, Martin, for the nice presentation. I was just wondering about the impact of the number of clusters, because in the motivating example, the robust clustering, you assume you know the right number of clusters, and in the final numerical results, you only got the k equal to 2. So I assume it's if you increase the number of clusters, things are getting even more difficult. So I don't know if you have done some simulation, or if you have any comment on that. Thank you.
Yeah. So hi, Salva, first of all. Well, I did not manage to give a talk on this topic without getting the question how to choose the K. So of course, this is super important. And throughout my entire talk, I assumed that the K is given, okay? In practice, people usually try to figure out what K is using some cross-validation techniques, okay? But for everything that I was talking about here, I just assumed that it was given. You might think, okay, K equals 2 might sound ridiculously small for the data that I showed you before. And this is true. So this is an obvious and very valid criticism on this work. We should also go to larger Ks. The problem is that the larger the K gets, the more difficult it gets to solve these problems to global optimality. So really going to larger Ks is one of the super open topics in global optimization on the MSSC problem, in my point of view. There was, okay. I hope this answered the question already, a bit at least. I mean, it was.
Yeah, I don't know if I don't know if the other approaches, this semi-definite programming, are also around this number of clusters as well. So that's like
well, I mean, they can solve larger instances, right? I explicitly talked about the paper by Veronica Picchiali and co-authors that they published, I think, 2 years ago. This is, from what I know, the state of the art, and they can also solve not only instances with larger sets of data points, but also larger K. But still, also for them, the K is actually crucial. If it's getting too large, they also have issues. So this is.
okay.
This is still open. Oliver in the chat, I just see this because I think this is related, also asked if the K can be part of the decision variables. Yes, of course, you can model this, but I mean, we tried this a bit. The models that you get are completely unsolvable in practice. So of course you can model this, but it's, wow, super hard to solve. Does this then, yeah, so Oliver writes, okay, thanks. So yeah, it's possible, but it's theoretically possible and practically impossible right now. This would be my answer. Yeah.
Yes, and Eligius, would you, yeah, so Nuria, could you give the rights to the camera and the microphone?
Okay, Martin, do you hear me?
Yes, hi.
Okay, so I missed in the beginning of the story, because you have shown the basic model, I missed the story about how you're dealing with symmetry, no? Because we know that we can reorder the cluster, but you didn't say anything about it.
Yes, we did this. I mean, maybe for the others as well. The problem is highly symmetric in the sense of integer programming symmetry, in the sense that whenever you have a solution, every, let's say, permutation of renaming of the clusters is a solution of the same quality, of course. So what we did in SCIP when we implemented all our techniques, we used also symmetry breaking techniques in SCIP that they are already there to break these symmetries. So it's not that the problems are so hard to solve, in my opinion, because they are so symmetric, because this can easily be broken.
Exactly. Yeah, you didn't kill SCIP because of that. That's nice.
No, it's really like the dual bound. Due to everything being feasible, it's really the dual bound that is always extremely bad when you use the classic solvers. By the way, we also tried other solvers. We also tried a bit of Baron and so on. So it's not just because SCIP is not strong enough at that point. It is really intrinsically hard.
It's very interesting. Very good. And that I had a second question about, because you said in the beginning you didn't like statistics, and 40 years ago they put a lot of statistics in my head. So then I realized recently that these Gaussian mixture models are used a lot. Okay, you were aware of that.
That's true. My colleague that I showed at the beginning is from statistics. He mentioned this as well. But maybe I have to correct myself also. I didn't want to say that I don't like statistics or stochastics. The correct statement is that I'm just not smart enough to understand what the people are doing, so that I have to do something different. That's the real story.
It's just probability. That's it. Thanks.
Yeah.
Thank you very much, Eligius. Yeah. So yeah, I think there are some comments about the elbow. Yeah. So which are it's something we could do, and obviously there are some comments about different models for different purposes. And there is a question here about usually when the robust counterpart is rewritten as a deterministic version, the number of optimization variables becomes much larger. Is this situation acceptable from a computation time perspective?
I think yes. I mean, the comment is correct in the sense that you get larger models if you apply the classic dualization tricks in robust optimization, for sure. But this is not the most severe reason for the hardness of the problems, because even the nominal problems are as hard to be solved as the other ones, almost. Yeah, it stays in the same order of magnitude. It's again really about the dual bounds. This is also why the STP approach right now is kind of the state of the art, in my opinion, because the STP bounds that you get are much stronger than the other bounds that you usually get from, let's say, LP based or convex relaxation based branch and bound.
Okay. So thank you so much. So I think we have handled all the questions in the chat. I will, is there any other question? So if not, then I think I will again like to thank you for making the time to come and talk to us. And thank you so much for the audience for the interesting questions. And we come back next week again on Monday. Yeah.